Hello, everyone. Let's solve some system of linear equations using the Gauss-Jordan elimination algorithm. Let's go. For our next example, we have a system of linear equations with three equations and four unknowns, w, x, y, and z. So already, if I ask you what is the number of variable for that system, you can write 4. So if we can use this number later, we will. So again, as usual, as soon as you have a system of linear equations, you construct the augmented matrix. So just by reading your system, we have 1w plus 2x plus 1y plus 1z equal to 1. That gives you your first row of your augmented matrix. Then for the second row, 2w plus 4x plus 3y plus 3z equal to 3. That gives you your second row. And finally, minus 3w minus 6x minus 2y minus 3z equal to minus 2. And that's your last row. So take your time. I know this sounds maybe easy, but if you make a mistake at that level, whatever you do with your augmented matrix will poison your solution. All right, so we're looking for our first pivot on our first row. What a coincidence here. On my first row, first column, I already have a 1 because life is great for me. So what I'm going to do is I'm going to do 2 eliminations to destroy the entries below that 1. I don't want to see any W in equation 2 or 3. So what do you do for that 2 in equation 2 or row 2? Well, you're just going to go row 2 will be row 2 minus, row 2 will be row 2 minus 2 row 1. That will get rid of that 2. And that for that minus 3, we're just going to go row 3 is row 3 plus 3 times row 1. Remember, I'm always using my future pivot as my eliminator. So again here, when I'm doing these things, anything that does not change, I like to rewrite quickly but carefully. So my first row is written again, untouched, no change. I know my first entry here is going to be my pivot. So now I'm going to compute the rest. So for the rest now, I have 2 minus 2 times 1. Of course, you're getting your 0. That was the point. So 4 minus 2 times 2, that gives you that 0 here again. 3 minus 2 times 1, that will give you a 1. 3 minus 2 times 1, that will give you a 1 again. No surprise now. 3 minus 2 times 1, that's my 1. That's my result for my first row. And then again, the first column for the third row, minus 3 plus 3 times 1, that gives you 0. Of course, you want zeros here in the first column. That was the point of those two elimination. Then you continue, minus 6 plus 3 times 2, we get 0 again. Minus 2 plus 3 times 1, that's a 1. Minus 3 plus 2 times 1, plus 3 times 1, sorry, is 0. And minus 2 plus 3 times 1, that gives you a 1. Now we're looking for our next pivot in the second row. Like I said, I like to put that little wiggly line. I'm not going to use row 1 for a while. So the first row with non-zero entry is the third column. And because I have already a 1 in that first, in that second row, this is going to be my pivot. And I'm going to do a simple elimination to get rid of the 1 under by using the following elimination. So I want to get rid of that 1 in row 3. So row 3 will turn into row 3 minus row 2. Again, I'm not using row 1. Even if you want, resist the temptation. This is going to undo your work. You're going to reintroduce stuff in the first two columns. You don't want to use row 1. We're constructing a pivot in row 2. Now, again, this is something I like to do, but for me, I like to rewrite the rows that I'm not changing. So not changing row 1, not changing row 2. So there's no operations on those two. So I like to rewrite them quickly, but carefully. So I have my future pivot, and then I actually do my operations. So when you do your operations, so we're working on the third row, you can start right away. So row. So sorry, got confused there. Hello. Sorry. There we go. So the one that I want to eliminate I get rid of it by saying 1 - 1. So that's how I get my 0. 0 minus 1. This is how I got -1 here. And 1 minus 1. This is how I get my 0. And my next pivot in the last row is going to be that -1. And actually, at this point, I have a matrix in echelon form. Oh, yeah. So I like to stop there and make those remarks because as soon as you get echelon form, you can comment on the general solution. So how many pivots do we have in the A part? I have 3 of them. How many in total? I still have 3 of them. When these two are equal, this means that we have some solution. So it's unique or infinite. But you can see here that 4, the number variable, is bigger than the rank numbers. So because it's bigger, we have infinitely many solutions. So we have infinite solutions in that system. But I want, and you could extract like the general solution from that echelon form. If the question was just to get a solution or the solutions, you can do it from echelon form. But because I'm evil, I'm always going to ask you to write your matrix in row reduced echelon form. So again here, the next thing I like to do is make sure that all my pivots are equal to 1. Right now, there's only one that is not equal to 1, and it's the third one. So I'm going to rescale it by multiplying it by -1. So I'm going to say row 3. So row 3, hello, okay, row 3 will become row 3 multiplied by -1 or divided by, but that doesn't change anything. So here again, very quickly, first row untouched, second row untouched, and I'm just multiplying the last row by -1, which affects only one entry. And now all my pivots at this point, all my pivots are equal to 1. So now I have to do elimination to make sure that these pivots are alone in their respective columns. Always starts for the rightmost one. This will minimize the number of computations. So I want to get rid of the 2 ones on top of the last pivot, the rightmost one. So I'm going to do 2 eliminations. So row 1 will be row 1 minus row 3. This is how I'm going to get rid of that one on the first row. And then row 2 will become row 2 minus row 3. Again, here notice that I'm always using the pivot for, or multiple of that pivot for my eliminations. So here the only row not changing is the last row. So I can rewrite that row 3 quickly, but carefully. And of course, the 2 entries on top of the last pivot are going to be zeros by construction. So you choose these eliminations to get rid of them. And because of those zeros, and this is why you go from the right to the left, because of those zeros, all the entries on top, so in row 2 and in row 1, are going to be unchanged because you're going to subtract zeros. So nothing is going on really for those entries and nothing is changing. The only true operation that you have to worry about is on the last column. But in this example, because I have a 0 also in the augmented part, then I just get my operation 1 minus 0 and 1 minus 0, and then just getting that last column unchanged also. And then, so just going to circle all my pivots. So I want to keep track of them. I need one more elimination to get rid of the 1 in top on top of the middle pivot. So I'm going to go row 1 becomes row 1 minus row 2. Now what will happen? Again here, I'm not changing the last 2 rows, so I like to rewrite these rows quickly but carefully. Of course, you're getting a 0 here. That was the point. And because of those 2 zeros here, those 2 entries will not change. Those 2 zeros playing in the fourth column, playing with each other, are not going to change. So the only operation that you're doing at the end of the day here is 1 minus 1 to get that 0. And that matrix, my friends, is in row reduce echelon form. So this is in row reduce echelon form. Oh yeah. Now we're ready to work and write our solution in canonical form. My advice, this is something I like to do, label your rows as equations. So my first equation will be, my first row will be for equation 1, my second row will be for equation 2, and my last row will be for equation 3. I also like to take the time to put the variables on top of each column in the coefficient part, so just to remember which variables is associated to which, because here we can see that we have a pivot in the column for W, we have a pivot in the column for Y, and we have a pivot in the column for Z. The only one that is pivot free is X, and actually this is what we're going to use to identify our free variable. So our first free variable, the only free variable is X, so X is free. So we're going to say that X is equal to T, some real number. So remember, when you're assigning a number to a variable, a parameter to a variable, it means that you know what X is. It's anything you want. It's no longer an unknown. And now equation by equation, I'm going to figure out my other variables that are called the dependent variables or the link variable, depending on which literature you're using. So I like to start at the bottom just because I'm weird. Okay, so here, and I really like backward substitution, so I just like to pay homage to this. So when you read the third equation, that says 1z is equal to 0. So that's my solution for z. And if you read the second equation, we have 1y equal to 1. So we get specific values for those. And then for the last variable, or for the first equation, so for the first equation here, we have 1w plus 2x, now freshly known to be t, plus 0y plus 0z is equal to 0. So if you isolate w here, well, it's squeezed in, but if you isolate w, you get minus 2t. So now we have a formula for every single variable. So what we can do now is assemble these variables and write the general solution in general form. So we're going to bring this together. So I rewrote everything for you on the next slide here. So my free variable x, z is 0, y is 1, and w is minus 2t. And the first thing I'm doing is I'm assembling everything. So here, variable assemble, so w, x, y, z, minus 2t, t, 1, and 0. And remember, I'm always going to ask you to break this general solution in canonical form. That's the right way to present your solutions. So I need two column matrices, one for the constant and one for the multiples of t. So when I read my first equation for w, I have 0. I know I have 0 minus 2t. So that's how I break my first equation. For x, I have 0 plus 1t. For y, I have 1 plus 0t. And for z, I have 0 plus 0t. And that's my general solution in canonical form. Remember, as soon as you have one free variable or more, you have infinitely many solutions. All right, for that example, that's it. So for this video, that's it. That's all. Bye-bye.